Welcome back to the deep dive. Usually when we start digging into these tech stacks, we're looking at code snippets or architectural diagrams right off the bat. But today, I want to start with a question that really stopped me in my tracks while I was reading through our source material. We have this persona in the text, the code architect, and he poses this question. Ever wondered how Netflix handles millions of streaming requests without blinking?
It is a staggering number. I mean, when you actually try to
Yeah.
visualize it, millions of people hitting play at the exact same second.
Right. And my brain immediately goes to hardware. I'm thinking, they must have the world's biggest supercomputer somewhere in a basement. But the code architect pivots right away. He says it's not just about raw power, it's about message queues. And that, specifically, is our mission today. We are going to unpack the high-stakes world of system design to understand how we move from systems that crash the second they get popular to these robust architectures using tools like Kafka and RabbitMQ.
Exactly. We're essentially dissecting the difference between a fragile system and an anti-fragile one. And while Netflix is the flashy, Hollywood example, the source material actually grounds this in a scenario that I think every developer and honestly every business owner has nightmares about.
The flash sale.
The flash sale, the dreaded Black Friday scenario.
The sources paint a very, very vivid picture here. So imagine an e-commerce platform. You've got a limited sneaker drop or maybe concert tickets for the biggest tour of the year. Traffic just spikes vertically. We aren't talking a gentle curve. We are talking a wall of traffic. And suddenly, order processing grinds to a halt.
The spinning wheel of death.
Exactly. Payment failures start skyrocketing. Users are getting timed out. They're frustrated. They abandon their carts. And the bottom line is revenue, which should be peaking, actually plummets because nobody can check out. And what I found so compelling in the reading is that this isn't necessarily because the servers are broken in the sense that they, caught fire. It's about how they talk to each other. The source describes this as an architecture of failure. That sounds dramatic, but can we break down what that actually looks like?
Let's do it. So looking at the diagrams provided in the research.
The one labeled pattern A plus pattern B.
That's the one. We see a classic flow. You have the client, they hit the API gateway, then that goes to the order service, then the payment service, then the database.
It looks like a straight line. Very logical. Step 1, step 2, step 3.
It is logical, and that's why so many systems start this way. But that straight line is what we call a synchronous system. It's tightly coupled. Think of it like a bucket brigade putting out a fire.
Okay, let's unpack that analogy.
In a bucket brigade, you hand the bucket to the next person. If the person next to you drops the bucket, or if they just stop moving to tie their shoe, you are stuck holding your bucket. You can't move.
Right.
That is exactly what happens in a synchronous software system. The order service accepts a request, but it cannot say job done until the payment service finishes its job. And the payment service might be waiting on the inventory service.
So if I'm the order service, I'm basically holding the phone line open, just waiting for the payment service to pick up.
Correct. You are holding that connection open, which means you're holding onto memory, CPU threads, resources. You are paralyzed until the downstream service responds.
And that's the trap, because if the payment service gets just a little bit slow, maybe the bank API is lagging, the order service is stuck waiting.
It creates a bottleneck.
Yeah.
And the source material highlights these red arrows appearing in the diagram, calling them cascading failures.
Cascading is the key word there.
It is, because everything is coupled together. A delay in the database ripples all the way back to the user. If the database adds, say, 200 milliseconds of latency, the payment service waits 200 milliseconds. The order service waits. The API gateway waits. And suddenly, your entire system is clogged.
It's like a traffic jam. One car braking on the highway causes a standstill 5 miles back.
Exactly that. So you have a system that works perfectly fine when 5 people are buying socks. But when 5 million people want that new gaming console, the whole thing collapses under its own weight because everyone is waiting on everyone else.
So that's the architecture of failure. It's fragile. Now, let's pivot to the hero of our story, the message queue. The outline calls this section the solution, which promises quite a lot. We're talking about decoupling.
Decoupling is the magic word of this entire deep dive. The goal is to explore how we move from that fragile bucket brigade to a robust asynchronous fortress.
So introduce us to the new cast of characters. We aren't just dealing with services calling each other directly anymore. The source introduces producers and consumers.
Right. So in this new architecture, using something like Kafka or RabbitMQ, we change the rules of engagement. When you place an order, The order service doesn't turn around and tap the payment service on the shoulder and wait for a response.
It does.
No, the order service acts as a producer. It takes that order data, the message, and it sends it to the message queue, and then it moves on.
It just drops it off, like dropping a letter in a mailbox.
Precisely like a mailbox.
Yep.
It says, here is an order, drops it in the queue, and immediately turns back around to accept the next order from the next customer.
Oh, I see the massive shift here. So the order service isn't waiting for the payment service anymore. It isn't waiting for the bank. It's completely independent.
Independent, that is decoupling. The order service can take thousands of orders a second because all it has to do is write a quick note to the queue. Then on the other side of the queue, you have the consumers. These are your payment services, your inventory services. They pick up the messages from the queue and process them.
But they process them at their own pace.
Asynchronously. That's the key. If the payment service is running a split second slower than the order service, it doesn't matter. The order service keeps taking orders, the queue holds the messages, it's a buffer, and the payment service works through them as fast as it can.
So instead of a blocked pipe where everything bursts, it's more like a reservoir.
A reservoir or a holding tank.
Yeah.
You are smoothing out the spikes in traffic. You accept the flood of water, hold it, and let it drain out at a safe, manageable speed.
So the user gets a "thanks for your order" screen instantly, even if the inventory hasn't officially updated in the database yet.
Exactly. And for the user, that feels incredibly fast. Wow, instant checkout.
Well,
And for the business, it means you aren't turning people away just because the database is taking an extra 50 milliseconds to write a record. You capture the revenue.
okay, so that's the concept. Decoupling saves the sale. But the source material really wants us to get technical here. It specifically zooms in on Kafka as the tool of choice for this high-scale stuff.
Kafka is the heavy hitter. It's the industry standard for a reason.
The source defines it as a distributed, fault-tolerant streaming platform, which is a mouthful, and it throws some specific vocabulary at us. Brokers, topics, partitions. I want to break these down so we can really visualize the machine.
Let's build the mental model.
Visualizing the diagram in the source, we have the Kafka cluster. What are the brokers?
Think of the brokers as the servers. They are the physical or, virtual machines that act as the storage managers. They are the post office workers sorting the mail. They hold the data on their hard drives.
Okay, so broker equals server. And the topics.
The topic is the category. In our e-commerce example, new orders would be a topic. User signups might be another topic. Payment confirmations, another. The producers write data to a specific topic.
Simple enough. But here's where the source material suggests it gets really interesting. Partitions. The text makes a big deal about topics being divided into partitions distributed across brokers. Why does slicing it up matter so much?
This is where we get to the scalability promise of the deep dive. Imagine a topic is just a single log file on a single computer.
Right.
No matter how fast that computer is, there is a physical limit to how fast you can write to it. A single disk can only spin so fast. A single network cable can only carry so much data.
It's a speed limit.
Exactly. By splitting a topic into partitions and putting those partitions on different brokers, you unlock parallelism.
Explain that.
Instead of one line at the grocery store, you open 10 lines. You can have multiple consumers reading for the different partitions at the exact same time.
So we aren't just processing one order after another. We're processing 10, 20, or 100 orders simultaneously.
The power of parallelism.
Yeah.
The source actually gives us a specific metric here that blew my mind. It mentions increasing order processing speed from 1,000 orders per second to 10,000 orders per second.
That is a 10x increase.
And that creates a massive competitive advantage. That is purely because of partitioning. Instead of one consumer reading the list one by one, you have an army of consumers just eating through that backlog.
So going back to our flash sale, that is the difference between crashing and setting a sales record.
It absolutely is.
Yeah.
But, and there's always a but in system design, there's a nuance here that the source points out.
Oh, I caught that too. Ordering is guaranteed within a partition.
Yes. This is a classic gotcha. If you have 10 checkout lanes, 10 partitions, you cannot guarantee that the guy in lane 1 will finish before the guy in lane 5.
Right. Lane 5 might have a faster cashier.
Exactly. Now, for some things, that doesn't matter. But imagine if you send two messages. Message A is create account, and message B is add funds to account.
If add funds gets processed before create account.
The system crashes. It says account does not exist.
Disaster.
So the source explains you have to be clever. You use what's called a partition key. You ensure that all messages regarding the same user ID always go to the same partition.
So my create account and my ad funds are guaranteed to be in the same lane, one after the other.
Correct. You preserve the order where it matters for that specific customer while still running all the other customers in parallel lanes.
That is smart. It's optimizing for speed without breaking the logic.
Precisely.
Okay, so we have speed, which is scalability. We have decoupling. But the source outlines 3 pillars: decoupling, scalability, and resilience. Let's talk about resilience. Because if I'm dropping my order into a queue and walking away, what happens if the queue breaks?
That is the fear, right? I sent the message. Did it get lost in the ether?
Exactly. I don't want my order to disappear into the digital void.
So Kafka handles this with replication. The source mentions a specific setting. Replication factor equals 3.
What does that mean in plain English?
It means every piece of data, every single order that comes in, is copied to 3 different places.
3 different brokers.
Right. 1 is the leader and 2 are followers. If the leader fails, the power goes out, the hard drive spins down, the server catches fire, the system doesn't panic, one of the replicas immediately takes over.
Automatic failover.
It ensures high availability, you don't lose the data, you don't stop the service. The users never even know a server died.
And there was another setting mentioned for the producers. Ax all.
Acknowledgements equals all. This is the guarantee part. When a producer sends a message, it doesn't just hope for the best. With Axol, it waits for the system to say, okay, I have this, and all the replicas have this. You are safe to proceed.
That sounds like it might slow things down a tiny bit.
It does add a tiny bit of latency, but for financial transactions,
Non-negotiable.
you trade a few milliseconds of speed for the absolute guarantee that you will not lose that credit card transaction.
Speaking of things breaking, the source brings up circuit breakers. Now, I know what that is in my house. If I plug in too many heaters, the power cuts to save the wiring. Is it the same concept here?
Very similar.
Yes.
In a software context, a circuit breaker is usually installed on the consumer side. Let's say the database that the payment service uses goes down.
Okay, so the database is dead.
Without a circuit breaker, the payment service keeps trying to write to the database. It tries, fails, tries again, fails. It waits for timeouts, it consumes resources. It effectively hammers the already dead database.
It's kicking it while it's down.
Exactly. And it backs up the queue. So a circuit breaker detects that failures are happening, it trips open, it stops the flow, it says, whoa, the database is down. Let's stop trying for a minute.
So it gives the downstream system a chance to breathe and recover.
Exactly. It prevents that cascading failure. It fails fast instead of failing slow and dragging everyone else down.
But wait, if the circuit breaker trips and we stop processing, what happens to the orders? Do we just delete them?
Never. We never delete data. That brings us to one of my favorite concepts in this deep dive, the dead letter queue.
The DLQ. It sounds ominous.
It sounds like a graveyard, but I like to think of it as a hospital triage unit.
How so?
The source uses the example of an inventory service failing to process an item. Maybe the data is corrupted, or the item ID doesn't exist. It's a bad message.
And if the system keeps trying to process that bad order, it clogs up the pipes, right?
It's called a poison pill. They can block everything behind it.
So the DLQ is the solution.
Instead of crashing or blocking, the system takes that failed message and moves it to the dead letter queue. It essentially says, I can't handle this right now. I'm putting it in the sidebar.
And the main queue keeps moving?
The main queue keeps flowing perfectly. And the best part, that message in the DLQ isn't lost. It allows for later analysis.
So an engineer can look at it later.
Exactly. An engineer can look at the DLQ, figure out why the order failed, fix the data, and then push it back through the system.
Ensuring no data loss, even when individual components fail.
That is incredibly reassuring. It feels like every layer of this architecture is designed to expect failure and handle it gracefully.
That is the core philosophy of modern system design. You don't build systems that never fail, you build systems that survive failure.
Well put.
Now, to manage all this, you need to see what's happening. The source calls this observability, keeping the lights on.
You can't manage what you can't measure. The source mentions 2 industry-standard tools, Prometheus and Grafana.
Right. Prometheus for tracking the metrics and Grafana for the visualization, the fancy dashboards. But what are we actually looking at? The source lists some vital metrics.
The first one is queue depth.
How many messages are waiting?
Exactly. If that number keeps going up and never comes down, you have a problem. It means you are flooding.
Which relates to consumer lag.
Consumer lag tells you if your processing is keeping up with the intake. If the lag is growing, you might need to add more consumers. Remember that parallelism we talked about?
Right, spin up more servers to read the partitions.
Exactly. And then there is latency. The source cites a very specific target here. P99 latency less than 50 milliseconds.
What is P99? Why not just look at the average time?
Averages lie. If 99 requests take 1 millisecond and one request takes a whole minute, your average looks fine, but that one user is having a terrible time. P99 means looking at the 99th percentile, the slowest requests. If your P99 is under 50 meters, it means 99% of your users are getting a fast experience. It captures the outliers.
And broker health, obviously.
Right. Is the hard drive full? Is the CPU overheating? All the basics.
The big takeaway here for me is proactive resolution. The source says visualizing these metrics allows engineers to detect issues before they become outages.
If you see the queue depth creeping up, you can fix it before the customers even notice a slowdown. That is the difference between a frantic 3 a.m. wake-up call and a smooth operation.
So let's bring this all back together. We started with a fragile, synchronous e-commerce site. Pattern A plus pattern B, it was crashing, burning, and losing revenue during the flash sale.
The architecture of failure.
And we transformed it. We introduced message queues. We decoupled the services so the order service doesn't wait on anyone.
We added scalability with Kafka, using topics and partitions to go from 1,000 to 10,000 orders a second.
And we built in resilience. Replication to save the data, circuit breakers to save the services, and dead letter queues to save the failed messages.
It really is a fortress. It's a complete shift in mindset from do A, then do B, to an event-driven flow.
The source material ends with a visual of the code architect, pointing out that Kafka might be the missing piece. And after this conversation, I feel like that really lands.
It often is. When teams hit that wall where their database can't keep up or their API is too slow, this asynchronous architecture is the unlock.
And the source leaves us with a provocative thought to wrap up. We spent this whole time talking about e-commerce buying sneakers Black Friday. But the text claims this architecture is the invisible backbone of the modern internet.
It is everywhere. It's not just shopping.
Streaming, like the Netflix example we started with, banking, ride-sharing.
Think about it. When you request a ride on a rideshare app, you don't wait on a loading screen until a specific driver accepts.
That's true. I hit request, and I can go check my email while it searches.
You acted as a producer. You sent the request ride message. The system finds a driver asynchronously. If it was synchronous, your phone would be frozen until the driver said yes.
Banking transactions, social media feeds, logging data from millions of IoT devices, they all rely on this decoupled, scalable approach.
If the modern internet was synchronous, it would basically grind to a halt. Asynchronous processing is what allows the scale we live in today.
So the question for you listening right now is this. Where else in your world, whether it's your code, your business processes, or just how you organize your day, could asynchronous thinking solve a bottleneck?
Are you blocking your own progress, waiting for a synchronous response, when you could just send the message and move on?
Something to mull over. We will leave you with that. Thanks for diving deep with us today into the world of message queues.
It was a pleasure.
We'll see you on the next deep dive.